So here's a challenge to kind of get our day going. What if we wanted to go even lower? I have a question for you. Can you come up with a one-dimensional data matrix and a transformation that gives me back the original data? So before you captured this redundancy and made it three-dimensional instead of four. So how would I do it in one? Okay, that's a mean question. This is the first impossible question I've given, I think, so I made it red. So you can't do it. It's not possible. There's no way to do this. So why is it impossible to find a one-dimensional representation that can be transformed back into four? So give me an intuitive reason. Yeah. Yeah, are independent from each other. There's no relationship. I mean, unless there's some law in your country or whatever that says you must have a backyard that has this certain aspect ratio. So that's just not how things work. I think that's a great, wonderful argument. They're just fundamentally independent things. Okay, great. Okay, good. So we know it's impossible. And so now let's talk about how we can kind of do it, even though it's impossible. Okay, so that's going to be our goal. Our goal today will be to do approximately this impossible thing. Okay, so I'm going to do a little experiment with some data. So let's say we now have noisy measurements of our backyards. So we get the width and the length perfectly, just to keep things simple. But then there's a little bit of noise in the area and the perimeter measurements because that's just how it is. Like we use, I don't know, the people we hire aren't as good. They can't get it down to the exact integer. So a question for you, what is the rank of this matrix with this noise? So maybe first, with no noise, what was the rank of this matrix? 3, because the perimeter was redundant. Now that we've added a little noise, what do you think the rank will be? 4, yes. Indeed, it will be. Even this very small amount of noise means that the perimeter is no longer exactly 2 width times 2, well, I said h, so I guess I'll say L. Let's fix it. 2L. Okay? So it is no longer the case that it is exactly 2 width times 2 length. And so if we actually run, say, a rank identification procedure, any one you want, you will get back 4, not 3. But that seems a little silly, doesn't it? Like, I mean, it looks basically rank 3. It's just a little bit of noise. And of course, in real data, you're going to have a little bit of noise. You're not going to have exact integer precision. This is not the way the world works. So we want to deal with this. Okay. So if we do the singular value decomposition, let's see what we get back. Okay. So if we actually go through, I'm not going to do it here, but it's in the notebook. So webcast viewers who want to do this, let's see, where is it? Here. Okay. Here's my noisy rectangle. I get back everything. Okay, so it's there, but I'm going to do it in slide version. So when I do this process of getting back U sigma and V transpose, here I'm showing sigma as a matrix by itself. So these are our singular values. And we notice that in U sigma, if we look at this thing, what do we observe? What are some interesting things? Well, one of them is that the last column of U sigma is not quite 0. When we did it before, it was like 10 times 10 to the minus 16th, which for all intents and purposes is basically 0 on a modern computer. But here, we see with this little bit of noise, these are no longer very close to 0, but there's some other numbers. Okay. So are these useful? I don't know. What do you think? What's your sense? Like, what do these numbers capture in some sense, maybe? Like, you can think of these crudely as the noise, but we don't really need it. If we want to get back a pretty good reconstruction, we can still, even though it is not 0, even though the singular value is not 0, it's 0.03, we can still throw it away. And if we do this, if we just remove that last column of U sigma and the last row of V transpose like we did in the last lecture, we get a pretty good approximation. So here I've multiplied it out. So my original data looked like this: 8, 6, 48, 28. If I throw away that fourth thing that isn't quite 0, then what do we get back? Well, we get back a pretty close approximation. I mean, the width and the length and the area and the perimeter are all a little bit off, right? But it's pretty good. So any questions about this? Okay. So the observation here is adding noise makes it rank 4, but we can still do the same process and throw away the last piece of our decomposition. All right. So what we've just done here is what is known as a rank 3 approximation. So even though the actual matrix is rank 4, we've approximated it using just rank 3 information. We use 3 dimensions of U sigma. Okay? And so the way I think about this sometimes is that our original data, it wasn't rank 4 exactly. It was like, just a little bit more than 3. And so our rank 3 approximation will be very good. Okay? All right. So there's our original data and our rank 3 approximation. You add some noise. Guess what? If you try and reconstruct it using only the first 3 dimensions of U sigma, you get something pretty good. This is my original data. Okay. All right. Any questions before I do the next weird thing? Okay, great. So here's a question. What would happen if we now did a rank 2 approximation? That is, we know that our data really is, rank 3-ish. If we do a rank 2 approximation, that is, we use only the first 2 dimensions of U and the first 2 singular values and the first 2 rows of V transpose, what do we get back? Well, we'll get back something, right? I mean, it's, in fact, just for the sake of making it very clear what I'm doing, let's look at it in code. Okay, I know that we're mostly ignoring this, but here is the process by which one computes the rank 3 approximation. So this basically says use everything but the last column, everything but the last singular value, everything but the last row. This is the same thing where now I'm writing it slightly differently because I'm going to write what I do want. So before I'm saying use everything but the last, now I'm saying please use the first 2. So please use the first 2 columns of U, the first 2 singular values, and the first 2 rows of VT. And if I do that, it's just a numerical procedure, and I get back an error because I haven't run the things above. Okay, let's do it. Okay, cool. So when we run this thing, we see that we get back a matrix. Okay? And this matrix, depending on, or if we compare it to the original data, it's not totally terrible, right? I mean, it's in the right ballpark. That is, the width here is 8. We're predicting with the rank 2 approximation, or we're approximating it, saying that it's 7.46 or so. It's not saying like 4 million, right? So that's good. It's like vaguely in the right ballpark. And actually, we can even go one more level deep and do the rank 1 approximation. So here, we're saying I only want to use the first column of U, the first singular value, and the first row of VT. And yet we get back something that doesn't look totally, completely, insanely bad. Okay? Now, the reason this is interesting to me is that, I'll come back to that question because I want to tell you what I think is interesting about it. What's interesting about it is that we've basically done the impossible. We have created a one-dimensional, version of the data, so to speak, and a transformation that lifts it back up in 4 dimensions. Okay? So question then for you. Do you notice anything interesting here? So do you notice any interesting patterns? This is the rank 1 approximation. It's not the same as the original data, but it's kind of close. And so what do you notice about it? Anybody spot any relationships between the rows or the columns? Okay. Anybody notice anything? Yeah. Yeah, so the rows are multiples of each other. Okay. Anybody notice anything else? Yeah. Oh, interesting. So area looks like roughly 3 times width and height. Plus what? Oh, interesting. I didn't notice that one. All right, yeah. I'll make another note here, which is related. This is also that the columns are multiples of each other. So here, this is sort of the structure. The top statement here is about the structure of the data. And the bottom one is something you've observed about what it's doing. Okay? Interesting thought. All right. So to return to our point earlier, the reason I find this really interesting is that you can get some sense of what it's doing. This is a little bit of a clue. But actually what it's doing is, just to make sure this is absolutely totally clear, all we've done, it's very simple, actually. Okay, I know it's easy to get lost when there's all this jargon and math, but all we've done is, hopefully you agree that if we had the entire matrix U sigma and the entire matrix V transpose, that multiplying them back together would give you the original data exactly. However, I have decided to throw away the last 3 columns and the last 3 rows. And so in effect, the approximation that I'm building is just this first thing times this first column times this first row. Okay? So this 100 by 1 column vector here times this 1 by 4, it gives me back a 100 by 4. This matrix right here, it lifts, or this vector, whatever you want to call it, it lifts from 1D back up into 4 dimensions. Okay, and so if you look at this thing, this is the reason that the rows are all multiples of each other and the columns are all multiples of each other is because they're formed using this very simple process. Okay. All right. So that's kind of interesting, right? We can get back something that roughly approximates our data, and it should feel almost a little magical unless you're really good at linear algebra, in which case maybe it just seems sort of obvious. It's a little bit magical that we said earlier, width and height, they're independent things. They have nothing to do with each other, right? You can have any aspect ratio you want. You can have a yard that's 1,000,000 miles long and only an inch wide, right? Whatever you want. And yet, despite that fact, given this data, we're able to capture things with just 1 degree of freedom. Okay? And so we're going to be exploring this philosophically, but that's maybe the surprise that somehow we're able to do this. Okay? So just put differently, this singular value decomposition procedure, that impossible challenge on the red slide before, it can actually solve it. It's just that it's not an exact solution. It's just an approximation. So we can't do equals here. We don't have enough degrees of freedom because people can make any aspect ratio, any width and height. I don't know why I'm saying height. Sorry. You can think of length and height. Just turn sideways, and you're good to go. But you can pick those things independently. And as a result, this can only ever be an approximation unless everybody has the exact same width and height and area relationships.